Today I want to show you a little calculator trick for a very specific type of question. This should be a short video. Uh, so the question that I have in mind is about a function. It could be this function, for example, that represents the position of a particle moving through time. So x is the time, and the function represents the position of this particle. This is a topic that is called kinematics. So what you're supposed to know in terms of content is that if this function represents the position of the particle, then the derivative of this function represents the speed of the particle, and the second derivative represents the acceleration. This is in the formula booklet, by the way. So even if you don't find it intuitive that the derivative of the position should be speed and that the derivative of speed should be acceleration, the formula booklet is there to remind you of that. So anyway, these kinematic problems are always about calculus. They're always about derivatives and understanding what the derivatives mean in terms of the function. Things like when you look at the graph of that function, then the turning points are points where the derivative is zero, and the inflection points are when the second derivative is zero. That's what this kind of question is about. Because this is a paper 2 question meant to be done with a calculator, the first mistake that a lot of people make is to start taking the derivative of the function. And that's not conceptually a mistake, it is correct. It's just a mistake in terms of exam strategy, because you're trying to save time, you're trying to do things in the most efficient way possible, you're trying to make good use of the technology when appropriate, which, by the way, is one of the many things that the IB exam is intentionally testing for. It says so right here in the grade descriptors. That sentence that I've highlighted in yellow here, make efficient use of the calculator functionality. This means, among other things, that you are not going to take the derivative of a function when all you want is information about a certain point that the calculator can easily get for you. Because on top of all that, if you try to take the derivative, there's always the possibility that you make a mistake. There's always the possibility that, for example, you forget that the product rule is something that exists and needs to be applied whenever the function that you're differentiating has a product. So let's not even go there. We're not going to take the derivative. We're going to use the calculator functionality. So what the question is asking, this particular question, is to find the acceleration of the particle at the moment when it first changes direction. So conceptually, there is a bunch of things for you to understand here. First of all, what is the moment when this particle first changes direction? Well, it was going up and now it's going down. So it has changed direction right there in that point of local maximum. So the question is about that moment. So the first thing that we can do is to figure out what the moment is, like how many seconds. This is not the trick I want to show you, by the way. This is more basic, but let's do it. You go into the second calc menu, ask it to find the maximum point of the function, and then it asks you for the left bound. So you go to the left of the maximum point that you want, click enter. Now he asks you for a right bound, you go over here and enter. Then he asks you for a guess, doesn't matter if your guess is good or bad, makes no difference whatsoever. That is the answer. X equals 1.52, I'm going to use it to 3 significant figures, is the moment when this particle first changes direction. Apparently, from what I can see in this graph, it's going to change direction again sometime later, but I'm not interested in that. The question was, what is the acceleration of the particle at the moment that it first changes direction? So acceleration is about the second derivative. Of course, he's not going to ask me what is the speed of the particle when it changes direction, because that has an obvious answer. The speed is zero when I'm changing direction. I have to stop in order to go the other way. But he's asking for the acceleration. If he was asking for the speed, then I could get that in the same menu. Of course, I'm assuming you already know this, but second calc, you can ask for the derivative of this function at a certain point, which in this scenario is representing the speed. And the funny thing about using this part of the menu, where you can get the value of the derivative of the function at a point, is that it doesn't explicitly ask you for the point here, but what you should do here still is to give the point that you want. And that is really funny because you have to give him the point where you want the derivative without him asking you for it. So once again, that's dy dx over here, enter. Now I'm going to put the 152 that I had from before, 1.52, and the answer should be 0 because that is the turning point. The only reason why it's not being a perfect 0 is because 1.52 is an approximation, right? I did not write down more digits than that. But the thing is that this is not what I want in this question. I want the acceleration. And I do have this menu to find the first derivative at a point, which is the speed, but I don't have a menu here to find the second derivative at a point, which is the acceleration. But what I want to do is to graph another function together with that one. I want to graph the derivative function so that then I can ask this menu for the derivative of the derivative, which is then going to be the second derivative of the original function. I'm going to say this again because conceptually this is the important part, so you do have to understand this. I am looking for the second derivative at a point. I only have a tool that gives me the first derivative. So I'm not going to ask for the derivative of this function at that point. I'm going to ask for the derivative of the derivative function at that same point. So that will give me the second derivative, which is the acceleration that I want. Okay, but this is the reason why a lot of students at this point think, well, even though this is a paper 2 question, I am going to have to pick up pen and paper and write down what the derivative of this function is. I'm going to have to use the product rule so that I can come here on the second line and type the function that is the derivative of that. But that's the trick that I want to show you. You don't have to take the derivative of this function in order to type it if the result that you want is just to see the graph. What you can do is to go here in the math button where you have, among other things, you have the derivative of a function. You can choose that, and it's pretty much the same notation as it would be if you were using this button outside of this functions screen. So you just want ddx, and here you want your original function, but you don't need to type the whole thing again because you've already typed it and it's called y1 now. So you need to put the y1 in there. There's a way to do that. If you see that green F4 thing up there, let's reach that. Green button, F4. Then it opens up this list. You can choose whichever one you want. Of course, I want to choose y1 because I want ddx of the thing that is currently called y1, and I want that at a point because this menu that came from the math button is not to take the derivative analytically. It's not to use the product rule and whatever. It's just to calculate numerically the value of the derivative at a point. But I want it as a function. I don't want just one point. I want all points so that it creates a graph. So my point is x. So it looks really weird in terms of notation because it says x equals x. But that is just the way that the calculator works. So now let's look at that graph. There you go. That is the derivative function. And now I'm looking at both of them, and I didn't have to calculate any derivative by hand. I'm still going to look at it a little bit to try to convince you that the red thing that we're seeing is actually the derivative function of the blue one. So let's look at some key points. For example, the local maximum. The derivative should be 0. And there you go, the derivative is 0. So what else? The turning point of the derivative, that should match an inflection point of the original function. And yeah, that looks like an inflection point, right? You sort of see concavity up before here and concavity down after that. So the red one is the speed function. The blue one is the position function. Red is the speed function. But what I want is the acceleration at point 1.52. So I am going to use the second calc menu to ask for the derivative, but I want the derivative of the red function, right? Right now it's clearly looking at the blue function, so let's change it to the red function. And remember that it's not going to ask me for the value of x. I just have to tell it that it's 1.52 without being asked. So there you go. The derivative of the derivative function at that point is negative 8.92. So that is the acceleration of the particle at that point. In theory, there is another way that you could have done this, because if I used this trick here in the screen to make the red function be the derivative of the blue function, there's nothing stopping me going one step further and making the black function be the derivative of the red function. Then I would have the black function be the acceleration of the particle, and I could just ask the menu for the value of the black function at the point where x equals 1.52. That in theory works as well, so let's go through that. It's the math button. I want the derivative. I want it d dx. The function now is going to be y2, so I need to open my F4 menu, which is alpha F4. Now I'm going to pick up the y2 instead. Moving to the right, now I want x equals x again. There's nothing wrong with that. This works. Let's graph it. And then if you go into the menu second calc and ask for value of a function, this one that actually asks you for the value of x, which is 1.52. Well, that's the value of the blue function, but that's not what I want. I also don't want the value of the red function. I want the value of the black function, which is the same number, negative 8.92 that we had before. So that works. But the reason why I don't recommend you do that, well, let me try to show you. I'm going to ask him to graph again. I'm going to change the window a little bit so that he does all the graphing again. Watch it as it builds the graph. The thing is that the more derivatives you're asking it to take, the slower it is. This is not a problem here in the emulator that I'm using to show you in the video, because it's my computer doing the calculations, and computers are considerably faster than the actual calculator that you're going to have with you during your exam. Seriously, try it out if you want to see this. It's really slow. The first derivative is okay, but if you ask it to do a second derivative, then it gets really, really slow. It's almost like it's plotting one point at a time. And the reason why that is so slow is because just like you are not picking up the pen and paper and actually calculating the derivative, the calculator is also not doing that. In fact, this calculator is not even able to do that. It doesn't know how to take explicit derivatives, which is one of many reasons why I think this is a perfect calculator for using in exams. I know that there are other models of calculators which are also allowed in the IB exams, which are able to take derivatives explicitly, but you are not allowed to have that functionality turned on during the exams. So it is a different process of setting up the calculator properly for exams. You probably don't have to worry about that. Let your teacher handle it. But the fact is that the TI-84 doesn't even do that. So the reason why it's graphing so slowly, it's because when I ask it to plot the red function, which was the derivative of the blue function, what it's doing is something very similar to the definition of derivative, which is a limit of a delta y over a delta x, like as if it was the slope of a line, right? A rise over run. It's this basically, the definition of derivative from first principles. This is what the TI-84 is doing in order to plot that red graph. It's getting 2 points that are very, very close to each other. It's calculating the blue function here and dividing one by the other, and for very small intervals so that it looks like a limit as h goes to 0. And that just takes time when it has to do it over and over again for each point that it wants to plot. And that's why the second one, the black curve, takes even longer, because it not only needs to do that for each point, but the actual values that it's using to subtract from each other and then divide those points also have to come from a similar limit calculation. So it just gets very computationally intensive. So anyway, that was the trick that I wanted to show you. I hope that it's helpful. I'm going to replay the part of the video that is the actual trick, just to remind you to finish off this video. But since we are talking about the TI-84 and the fact that it doesn't do derivatives, I just want to mention that I really love this calculator. I know that the other models are more powerful. They do a lot of things, like, for example, take derivatives. But the thing is that having a calculator that is more powerful than your exam allows doesn't really compensate, because you're not going to be allowed to make use of those extra features. And so if you're buying a calculator for the exam, in my opinion, this one really is perfect. But what some people tend to argue is that, well, I'm not just buying a calculator for doing an exam. I'm buying a calculator to have in my life, to use for things in the future. And so I want the most powerful calculator that I can get. And that, to an extent, makes sense. But my opinion is that I don't really want to have a calculator for my life. I want to have this calculator to do this exam. And this also brings us back to a much, much older discussion, right? Like, since the dawn of time, children have asked their teachers, but why do I need to learn how to add 3-digit numbers? I don't know. If the calculator can do it for me. And teachers would answer, but you're not always going to have a calculator with you. Which of course turned out to be false, because we do all carry powerful computers in our pockets. But it is still important that humans learn how to do these things. It's not because we're going to do it in our daily lives. Of course, we are going to use the technologies. But the thing is that nobody's going to make the technology to do things if people don't know how to do things. So it's important that people learn how to do things. That's why we still learn how to take derivatives by hand, even though, well, not this calculator, but a bunch of calculators do know how to do that, because a human at some point knew how to program it to do so. But still, that's not the reason why I say that personally I don't want to have a calculator for my life. It's not because I don't want to use technology for calculating. I do that. But the thing is that I have my phone, I have apps, I have my computer, I have software running in my computer. What I don't want is to have a full object that is dedicated only to being a calculator. This is something that I think has a place in exam taking. For obvious reasons, we can't have students having their phones in an examination, but I don't really want a calculator for my life. So that's it. That's all I wanted to say for today. So let's replay the part of the video that shows you the trick of how to do this very useful thing that I just did with this function. and bye. But that's the trick that I want to show you. What you can do is to go here in the math button, where you have, among other things, you have the derivative of a function. You can choose that. So you just want d dx. And here you want your original function, but you don't need to type the whole thing again because you've already typed it. If you see that green F4 thing up there, let's reach that green button, F4. Then it opens up this list. You can choose whichever one you want. Of course, I want to choose Y1 because I want d dx of the thing that is currently called Y1, and I want that at a point, but I want it as a function. I don't want just one point. I want all points so that it creates a graph. So my point is x. So now let's look at that graph. There you go. The blue one is the position function, red is the speed function, but what I want is the acceleration at point 1.52. So I am going to use the second calc menu to ask for the derivative, but I want the derivative of the red function. It's not going to ask me for the value of x. I just have to tell it that it's 1.52 without being asked. So there you go. In theory, there is another way that you could have done this, because if I used this trick here in the screen to make the red function be the derivative of the blue function, there's nothing stopping me going one step further and making the black function be the derivative of the red function. So let's go through that. It's the math button. I want the derivative. I want it d dx. The function now is going to be y2, so I need to open my F4 menu, which is alpha F4. Now I'm going to pick up the y2 instead. Moving to the right, now I want x equals x again. And then if you go into the menu second calc and ask for value of a function, this one that actually asks you for the value of x, which is 1.52. Well, that's the value of the blue function, but that's not what I want. I also don't want the value of the red function. I want the value of the black function, which is the same number, negative 8.92 that we had before. So that works.